So now we're going to look at how we would solve that problem using the solver program within Excel. You'll see that this is the matrix that we had set up before, and here's the right-hand side we had set up before. And what we have to do to make this able to be solved by solver is we have to link the activities and the levels associated with the activities to how much money it makes, in this case, the objective function, and what it does to the constraints. So essentially what we're going to do is we're going to add a row, which I labeled here the answer row, and I'm adding a column, which is where I'm going to total up the total amount of the objective function and the total amount of the constraints so that we can compare those to the right-hand side. So the way I'm going to do that is if I wanted to, what I could say is if I wanted to add up total SEV here, I could say it's this cell, which is E28, times however many acres is in the answer for steer acres, plus cell F28 times however many acres are assigned to tree acres in cell F27. It turns out there's an easier way to do that. There's a sum product function which adds up and multiplies two arrays. And so in the sum product function, what I've set up here is sum product E27 through F27, which is the answer, with E28 to F28. So that's going to do exactly what we want. This times this plus this times this. Now you'll notice that I've locked it on the row 27 array. What that means is when I get to this point, I can simply drag this formula down, which also happened to copy the formats this time. And it always points to row 27, but it points to whatever row I'm on. So let me turn that back to a different color. So this one. So what that means is right here it's 27 versus row 29. So what's going to go here is 1 times how many acres are assigned to that plus 1 times how many acres are assigned to that. And so by setting up that sum product and locking it on the first row and dragging it down, I've got the right formula in each one of these. We can test whether it's working or not, because I can just put again some trial numbers here and see what happens. And it's saying that, gee, if I had 50 acres of steer and 1,400 acres of trees, that would make me $1,310,000. Unfortunately, it would use up 1,450 acres, which is more than I have. It would also cost me $213,000 in first year budget, which I don't have. But in fact, it would not use up all of my erosion. 0.2 times 50 plus 0.1 times 1,400 is just using up 150 tons of my 200 tons. So this detached coefficient matrix has now been modified so that goal-seek can handle it. So when I open the goal-seek box, then I'll be pointing it to where the answer cells are, where the objective function is, whether the objective is to maximize or minimize. And then I'll add constraints by saying constraint 1 would be this has to be less than this. Turns out these symbols I have here are just that. They're decorations. This allows me to look at my matrix and know what I'm doing. In Solver, I'll have to tell it whether these constraints are less than or equal to. It won't read those signs. If you haven't added Solver to your Excel sheet, it's under add-ins. What I'm going to do is I've already done the add-in on this, and so I will now look under data. That's where it's put it, and I have Solver sitting there. I believe on the this version of Excel, you can see there's add-ins, um, and under options, and you can see that here's the ones I have, and I've already added solver. It used to be down here. I then clicked it and said go, and that added solver to this. So I'll exit out of there, go back to data, and bring up solver. So solver is sort of like a pretty powerful version of GoalSeek. It can do many kinds of solutions. It can do nonlinear, evolutionary. It uses different algorithms. We want to make sure for what we're doing here that we're choosing to use linear programming. That gives us the kinds of answers we expect, and that's the way we set these problems up. So you can see here that first thing I have to tell it is, where's my objective? Well, my objective is in G28. So the goal is to maximize that cell, so I choose maximize. Which cells do I put the answer in, or what variables do I change to try to maximize SEV? I'll choose these two. That's where the answer is going to go. And then I'm going to add constraints. I could do this, but oops. Oh, I already had SCV in there, so when I just clicked it again, it put two versions in there. Looks like the changing variables are okay. And so when I add constraints, I could just do it one by one. I could say, all right, I want to add this constraint, so I want this cell to be, and here's my choices. This one is less than or equal to. I want it to be less than this cell. So G29 has to be less than or equal to I29, which is the acreage constraint. Since I've already added these constraints, I'm going to cancel out of this, and you can see the way I did it here was I actually said I want to add these three constraints. Since they're all less than or equal to, I can do that. They're all less than, and I want to make them less than these three right-hand sides. That works too, and that's what I did to get it set up that way. So I've got it pointing to my objective function. I've told it it's maximization. I've told it which cells to change. I've told it the three constraints it has to meet. I've told it to use linear programming, and now I'm going to hit solve. And it's solved. So we have this answer solved. Solver found a solution. All constraints and optimality conditions are satisfied. It's put the answer in the sheet. If I leave that button pressed, it will leave the answer there, and that's what I'm going to do. It has three sets of reports. The two sets of reports that we are most interested in are answer and sensitivity. Since I've already printed those reports out, I'm not going to ask for them again, but I will leave the solution in there. So I'll say OK. So now it's told me the answer, which luckily is the same that we got when we did the graph. Allocate 800 acres to steer, 400 acres to trees, make $1,160,000. Use all of your acres, use all of your erosion, but you don't spend all of your money. So the erosion constraint is not binding. If we look at the answer report for this problem, we can see that it tells us a lot of stuff about how it solved the problem. If we were doing multiple answers, it would tell us what our original answer was and what our new answer is. But it's there's $1,160,000. That's our objective cell max. Here's our final value for steer acres at 800. Our final answer for tree acres, 400. We have three constraints here. The acre constraint and erosion constraint are binding. The budget constraint has a value of 120,000. It is not binding, and it has a slack of 22,500. So as we've mentioned before, binding constraints have zero slack. Non-binding constraints have slack. That also means that when we look at the next sensitivity report, we should be able to find the shadow price for the binding constraints. So let's do that. Here's the sensitivity report for this problem. These cells over here give you an idea of how sensitive the answer is to the slopes of these cells. So how much you could increase or decrease these variables and change your answer. We won't play with that in this class. The shadow price, however, is something that I want you to pay attention to. Remember that the definition of a shadow price is how much the objective function would change if you increase the right-hand side of a constraint by 1 unit. So in this case, acres adding up, um, acres constraint has a shadow price of $800, which means that if we had 1,201 acres, we would have made $800 more, which means that we could buy land if land was cheap, or we could afford to pay $800 and come out ahead. We had 200 tons of erosion. If it was 201 tons of erosion, we would have made $1,000 more. That gives us some information that if we can maybe do some fairly costly erosion practices, as long as they're under $1,000, and all they have to do is prevent 1 ton of erosion, they might be worthwhile. So shadow prices are a pretty powerful source of information. So that's how to solve that problem. Excel, if we go back to the answer, you can see there's the graphical constraints and the combined binding constraints. So land and erosion are the binding constraints. If I ask you to add a constraint to this that would make it non-binding, then what you might could do is add a constraint, for example, that the minimum amount of steers that you consider is 1,300. If you added a constraint like that, then it would be a vertical line at 1,300 steers, and everything to the right of that would be in the feasible region. Unfortunately, there is no place that's to the right of that and meets these other constraints. So if you put that constraint in there, it would lead to a non-feasible solution. If I ask you to put in a constraint that would be non-binding, which means it would not change the answer would not be sitting on that line, then you could put in a minimum steer constraint for 200. In other words, I have to have at least 200 steer. That would be a vertical line here and everything to the right of that. That would change the feasible region shape to be just this part of the current feasible region, but it wouldn't change your answer. And it would be a non-binding constraint because it would have this much slack. In other words, we had the constraint to have at least 200 would have a slack of 600 because the optimal solution provides 800. So this is a way to get started on solver and linear programming, and I hope it helps.